These notes are over the force of friction. Okay, so if we were to consider, like here, this image of the apple sitting on a slanted surface and it's not moving, okay, we would expect that it would start moving due to the force of gravity kind of pulling it along the surface of the board. But what's preventing it from sliding down this slanted surface is friction. Okay, so friction is kind of important, and here it's kind of described as Jekyll and Hyde, just because we need friction to move. If we don't have friction to move, just like Newton's third law, for every action there's an equal and opposite reaction. Okay, friction is the whole reason why we can like walk across the floor or stuff like that. So if you've ever tried to like walk across a surface that has kind of less friction, like for example ice, you'll find that it's much harder to walk across the ice surface than it is across a floor or like a concrete floor. Okay, and the reason for that is due to friction. Okay, but on the flip side, friction also hinders our movement by causing the kinetic energy or the moving energy to turn into heat and cause wear and tear on objects. Okay, so we actually lose some of the kinetic energy to heat. Okay, so that's why friction can cause things to slow down, just depending on the situation. Okay, so friction is believed to be caused by these microscopic welds or microwelds. So all surfaces are not completely smooth. They all have these tiny little imperfections along their surfaces, and what happens is, depending on the number of these imperfections along the surface, the two objects that are touching form these little welds together as they contact. So it's kind of like puzzle pieces. And what we see is that when we have a static friction, which is when the object is not moving, it's actually greater than whenever the surfaces are being slid past each other, okay, or kinetic friction. And it has to do with the way that these two surfaces are interacting together, okay. So like I said, static friction occurs when the object is not moving. So examples of these, or like great examples of these, are like a car parked on a hill. The reason it doesn't roll down the hill is due to static friction. A box on a ramp, just kind of like the apple above, or like leaning against an object that does not move. Okay, whereas kinetic friction occurs when an object is moving. So like when you rub your hands together, you can feel the heat that's produced due to friction. Okay, objects being pushed across the floor, or a sled sliding on the snow. Okay, so for frictional force, there exists this coefficient of friction. And so that's if we don't choose to ignore friction. So up until this point, we've kind of ignored friction as far as the forces acting upon objects. Okay. Also, we know that there exists a normal force between two surfaces. Okay, so there is an applied force trying to move that object, and if any of these are not met, there's going to be no friction. Okay, so the coefficient of friction is this symbol here, and it is mu. So mu is the coefficient of friction symbol. So the coefficient of friction is just a value that shows the relationship between the force of friction and the normal force between two objects' surfaces. Okay, so the normal force is important here because the normal force in general, whenever we're kind of like thinking about surfaces and objects sitting on a surface, the normal force is generally going to equal the gravitational force that's pushing down on the object between the two surfaces. Okay, so with this, the more normal force you have, right, the greater a force between the two objects, the more friction you're going to experience compared to when you have less force between the two objects. Okay, so imagine you have two coins, one on smooth ice and one on rough plywood. If you flick it with equal force, which one is going to go further? And so what's nice is that you guys have already had life experiences that kind of let you know what would happen in this situation. Okay, so we would expect that the coin on the smooth ice would travel further because it's experiencing less opposing frictional force. Okay, so the coefficient of friction is determined by using the ratio between two forces. Okay, so mu is going to be different for different surfaces that are touching together. Okay, so to find it, it is the force of friction divided by the normal force. Okay, so it is the ratio of how much frictional force there is to the normal force. And so if we look at like the units for this, mu is the frictional force divided by the normal force, which are both in newtons. So if we were to divide these out, they would cancel so that we get 1. So mu is actually unitless. Okay, so to find the force of friction, we rearrange the previous equation to find that the force of friction equals mu times the normal force, okay? And so we can have mu of the static friction or mu of the kinetic friction, okay? And so remember, static is going to be stationary objects, kinetic is going to be moving objects, okay? And so here are some common coefficients of friction between different materials, okay? And you'll use this in your practice problems to find the coefficient or to utilize the coefficient of the different surfaces. So you'll notice there's one column that is for the static or non-moving objects, okay? And then one for the kinetic friction or moving objects, okay? And one thing to note too, if you look between these, okay, the static friction is generally greater than the kinetic friction, okay? And you've probably experienced this in your life experiences as well. So if you have a big heavy box, okay, and you go to push it across the floor, it's probably a lot harder to get it to start to move, but once it starts moving, it's much easier to slide, okay? And that's just because of these differences in coefficients. So static friction is generally always going to be greater, either equal to or greater than the kinetic friction, okay? And that's just because the microwelds have really been able to kind of snap together, kind of like puzzle pieces, so it's harder to break those. Then whenever it's already moving, they don't have enough time to really make those connections as well. Okay, so what you should see from this table is that most of the values range between 0 and 1. We do have like one kind of exception here, but for the most part, that's how they fall. Okay, and we would expect a small value for mu whenever we have smooth surfaces. So like Teflon and Teflon, they actually have very similar, or they do have the same coefficient for both the static and the kinetic friction. So Teflon is kind of like the non-stick surfaces of like cooking utensils and things like that. So they're expected to be very, very smooth to have low friction coefficient. Okay, and then we would expect a large value for mu between rough or sticky surfaces. So for example, like the leather and rock or the rubber and concrete. Okay, so it's like a stickier substance and a rough surface. For a stationary object to move, the force applied must be greater than the force of static friction. Okay, and so remember with friction, when we calculate it, that's the greatest it can be. So it changes based on the force that's being applied to it. Okay, so in order to overcome it and actually move the object, the force applied has to be greater than the static friction. Okay, so for example number 1, a pack of dogs are pulling a wooden sled and rider of combined mass of 238 kilograms across dry snow. How much force did the dogs need to apply to cause the sled to begin to move? Okay, so for this, we're going to draw out the free body diagram. Okay, so I'm going to start with my gravitational force and normal force. Okay, so the gravitational force is going to be pulling down on the object. Okay, where F of G is equal to the mass of the object times the acceleration due to gravity. So we would have that F of G equals our mass, which is 238, times gravity, 9.8 meters per second squared, and our F of G is going to be equal to negative 2,332.4 newtons, okay? And so because the object is not accelerating in the vertical plane, okay, it's not accelerating up or down, that means that the force of gravity is going to equal the normal force. So the normal force is going to have the same magnitude, just in the opposite direction. So our F of n is equal to 2,332.4 newtons, but in the upward direction. All right, and then we have our applied force, our F of A, that's applied by the dogs, and then the force working against that is our friction force, so our F of F. Okay, so if we are trying to overcome the static friction, the sled is stopped and the dogs need to pull it with enough force to get it to start moving, we're going to use the equation for the stationary static object. Okay, so that is our friction force is equal to the static friction coefficient times the normal force. Okay, so plugging in what we know, if you go back and look at the chart and find wood against dry snow, because those are the two surfaces that this problem gave to us, the coefficient is 0.22, okay, times our normal force, which is 2,332.4. Okay, and we'll find that the friction force is 513.128 newtons. Okay, so in order to get the sled moving, the force must be greater. Okay, so the applied force must be greater than 513.128 newtons. For question number 2, you push your 27-kilogram wooden desk across the wooden floor with a constant velocity. Find the friction or the force of friction and the applied force. Okay, so once again, I'm going to start with my gravitational force. Okay, is mass times the acceleration due to gravity. So when I plug in the known values, my mass is 27. Gravity is negative 9.8. So the force felt due to gravity is negative 264.6 newtons. Okay, because once again, we're not accelerating in the vertical plane, my normal force is going to equal my gravitational force in magnitude, just in the opposite direction. So we're going to have positive 264.6 newtons as our normal force. Okay, we are pushing with an applied force. Okay, and then friction, the frictional force, is working against our applied force. All right, for this problem, we're going at a constant velocity, so that means our acceleration is going to be 0. Okay, and so because of this, our applied force is going to equal our friction force, okay, because I'm not accelerating. If I was applying more force than the friction force, I would be accelerating in this case, to the right, okay? So because there's no acceleration, we're moving at a constant velocity, we know that F of A is going to equal F of F, okay? So in this problem, we are moving, so we need to use the kinetic coefficient of friction. Okay, so our force of friction is equal to the kinetic coefficient of friction times our normal force. So whenever we plug it in, if we look back at the chart, the wood against wood in the kinetic friction column is 0.2, and then times our normal force, 264.6 newtons. And we find that our friction force is 52.92 newtons. Okay, and that would be, in this case, to the left. Okay, so that means that our applied force is going to be 52.92 newtons to the right. Okay, so sometimes we perform calculations. The force of static friction is greater than that of the applied force. So you just have to be careful when drawing out these diagrams. The object will not move until the applied force is greater than the friction force of the static friction. Okay, so if two sisters are fighting over the contents of a 48 kilogram crate, one sister is pulling with a force of 79 newtons to the right, while the other pulls with a force of 51 newtons to the left. The coefficient of static friction between the crate and the floor is 0.32. Find the acceleration of the crate. Okay, or like I just said, if it's going to accelerate at all. Okay, it might not be enough force in order to move the box. Okay, so I'm going to start with my gravitational force and normal force, okay, because those are pretty simple. They're usually similar for most diagrams. So here I have my force of gravity, which is going to be equal to our mass times the gravitational constant here on Earth. Okay, so if I plug it in, 48 times negative 9.8, I get that my force of gravity is negative 470.4 newtons. Okay, so my normal force, because we're not accelerating in the vertical plane, is going to be equal to my gravitational force. Oops. Normal force. It's going to be 470.4 newtons, just in the opposite direction. All right, now I need to put in the forces that are applied by the sisters. So we have one sister who is pulling to the right with a force, so we'll call this F1, of 79 newtons. Okay, and then the second sister is pulling to the left, so we'll call her F of 2, with a force of 51 newtons. Okay, so if we were not looking at friction currently, and we were just looking at the two forces between the sisters, okay, we would expect that the box would accelerate towards the right because the force of the first sister is greater than the force of the second sister, okay? So because of that, and we should see that it's accelerating to the right, the force of friction is going to be acting in the left direction. So here is where our force of friction is going to be, okay? Because it's going to oppose the direction of acceleration, okay? So in this case, because the first sister is pulling with more force, we would expect that the acceleration would be to the right, so the force of friction is going to be acting in the opposite direction. So in order to move the crate, the net applied force would have to be greater than the static force, okay? So the net applied force would be adding the two vectors of the sisters in this case, okay? Because the f of n and the f of g, they cancel each other out. So really we're just looking as far as the applied force, adding the two sisters' forces together, okay? So if we go ahead and do that, so our applied net force is going to be F1 plus F2. Okay, and we'll say right is the positive force. So when we plug it in, F1 is going to be positive 79 plus our negative force, because it's going the opposite direction, of 51 newtons from this second sister. So we find that our applied net force is going to be 28 newtons. Okay, now we need to find what is the maximum friction force that could be felt by this object, by the crate. Okay, and so we're doing a non-moving crate, so we have to use the static friction coefficient. So the force of friction is equal to our static friction coefficient times our normal force. So F of F equals, they gave us the static friction coefficient of 0.32 times our normal force of 470.4, and we get that our force of friction is 150.528 newtons. Okay, so because our applied net force is only 28 newtons, and the most that our force of friction that can be experienced is 150, the girls are not able to accelerate the crate or get the crate to start moving, okay? So what happens is, because the box is not moving at all, we'll see that our friction force that's actually being felt is going to be equal to our F of A of net. Okay, so that we have an acceleration of 0. Just because, like I said again, this is not the force of friction that's being felt by the girls. If that was true, it would start accelerating in the left direction. Okay, so because, and I'll go ahead and give the directions to these. So this is to the right, this is to the left. Okay. If this was the friction force that was felt, like I said, it's going to accelerate in the left direction because it's way greater than the force of the applied, the net applied force. Okay, so what is going to be experienced in this case is that the frictional force is going to be equal to that of the applied net force, so that the object does not move.